Is the universe actually expanding? The theory that the universe is expanding from a central point that contained all the mass and motion of the entire universe focused into one tiny place and time was theorized in 1931 in a paper by Georges Lemaitre, a Belgian cosmologist and Catholic priest. Although this theory that the universe is expanding is largely accepted as true, we should keep an open mind and openly examine the history of this theory and any and all evidence in support or against this and every other theory without any restriction whatsoever. After all, the majority of people on Earth believed that the sun goes around the Earth for over 1,500 years, and well past the year Copernicus proposed that the Earth might go around the sun in 1543. So just because the majority of people believe something does not mean that it is true. But getting back to the theory of an expanding universe, before Lemaitre had, in 1931, formally published the theory of an expanding universe, Vesto Slipher had, in 1913, claimed that the Andromeda Galaxy is moving towards the Earth with an average velocity of 300 kilometers per second, 1/100th the speed of light. If true, this would easily be the highest velocity of an object ever observed at the time, besides the speed of cathode rays or the speed of light itself, of course. Slipher made this claim based on the theory that changes in the position of the visible spectrum of distant galaxies compared to the position of the spectrum of a local light source, in this case the spectrum of Saturn, are the result of the Doppler effect. The same effect the sound of a car makes when it drives past you, having higher frequency when approaching, but lower frequency when receding, but for a light-emitting object instead of for a sound-emitting object. In 1929, Edwin Hubble, using this same theory, had found what appeared to be a velocity-distance relationship for galaxies. The more distant a galaxy, the faster the galaxy seemed to be moving away from us. Milton Humason worked with Hubble at the Mount Wilson Observatory in Los Angeles, and in 1936 published more evidence thought to support the theory that the universe is expanding. In this work, Humason published black and white photographs of the spectra of 5 different galaxies that each appear to contain a calcium absorption line pair. Calcium atoms in between the stars and in the atmospheres of stars and galaxies absorb very particular frequencies of light, and this absorption results in the appearance in some galaxies, although not all galaxies, of 2 dark lines, typically in the blue region of the visible spectrum of light emitting from a galaxy. Humason found that in comparing these 5 spectra, that this pair of calcium absorption lines appeared to be shifted to the red, the right side of the spectrum, farther for the fainter and more distant galaxies, and less shifted for the brighter, closer galaxies. It is interesting to note that although color photography was available in 1935, Humason chose to publish black and white images instead of color images. The reason color images would help tremendously is to observe the color surrounding the calcium absorption lines, which could have provided instant confirmation of the actual frequency of the light surrounding the absorption lines, and show if the calcium lines had in fact changed frequency. The apparent shift of these calcium absorption lines implies that the most distant galaxies must be moving away from the viewer much faster than the closer galaxies are. It is important to note that this explanation is accepted by Humason's contemporary colleagues and presumably the vast majority of major astronomers of today as evidence that the universe is in fact expanding, that is, the more distant a galaxy is, the faster it appears to be moving away from us. However, with one glance at Humason's 1936 photo, it is easy to see a potential problem with this explanation. For one reason, all 5 of the spectra are different sizes, so it is no surprise that the calcium absorption lines appear to be shifted to the red part of the spectrum relative to the reference spectral lines from helium. Another important problem happens when we try to colorize these spectra. It is guesswork because we do not have a color photo, but because these are full visible spectra, they must contain one red-colored end and one violet-colored end. It is difficult to see where the violet end of the visible spectrum is in some of these spectra. If Humason tried to match the colors of the galactic spectra with the colors of the reference spectrum taken from helium gas, he did not explicitly mention that in this 1936 work, and clearly did not do a good job aligning the ends of the helium spectrum with the galaxy spectra. But trying to colorize these spectra just based on the relative size of each galaxy by dividing the different colors into equal-sized parts, we can see that the calcium absorption lines appear to be still located in the blue frequencies of the visible spectrum for all 5 galaxies. The color of light indicates what the frequency of light is. So in these spectra, there is apparently no change in frequency of the 2 calcium absorption lines. There is only a change in the size and position of the spectra on the grating. If we assume the colors of the 5 spectra are precisely aligned with the colors of the reference helium spectra, then notice how the bottom, most distant spectrum, while having its left blue end far away from the blue end of the helium reference lines, also appears to have its red end slightly blue shifted relative to the spectra from the closer galaxy above it. So it is obvious that the colors of the galaxy spectra, in particular for the bottommost spectrum, are not aligned with the colors of the helium reference lines, since the closer galaxy spectra appear to extend beyond the blue and red ends of the helium reference spectrum, while the farther galaxy spectra fall very short of the ends of the helium reference spectrum. Beyond this spectrum size problem, and the problem of the absorption lines not appearing to have changed their position relative to their surrounding color, there is another possible problem with the claim that spectral line position is due only to relative velocity of a light source, and that is that spectral line position also depends on the relative distance of a light source, as required by the equation for diffraction gratings, often called the Bragg equation. Take a look at these spectra of 2 desk lamps at different distances. Notice how the more distant lamp has a larger spectrum, and how the spectrum appears in a different position, farther to the red side of the grating than the closer desk lamp spectrum. This is the result of simple trigonometry. For example, say that the angle the light needs to make with the grating to produce blue light is 11 degrees. In that case, the right triangle formed by the light source and the grating shows that the blue spectral line at 11 degrees from a more distant light source must appear farther away from the center, 0 node, than the blue line from the closer light source is. In addition, because of this simple trigonometric relation, a more distant light source will have a larger, more spread out spectrum than a closer light source. In fact, this principle can be used to easily determine the relative distance to any light source simply by measuring how far any particular spectral line is from the center node on a grating, and comparing that distance to the same distance produced by the same color spectrum line from a different light source. We know the angle, and we know the distance from center to any particular color, and so using the tangent of the angle, we can determine the distance to the light source. You can easily just compare where the spectrum starts or ends for any galaxies. The closer to the center the blue end is, the closer the light source is. One thing to note is that if you do not use a slit to capture the spectrum, then you must subtract the radius of the light source from the spectrum end, because light sources have varying widths, which also affects spectrum size. So spectral line position changes depending on light source distance, and this makes no difference with regard to any relative motion of the light source. But Slipher, Hubble, and Humason never mention any awareness of this simple fact, that light source distance affects the position of the spectra, that generally speaking, the more distant a light source, the wider and more shifted to the outer red side part of the grating the spectrum appears. Would it be a very difficult undertaking to simply go back to revisit and repeat Slipher's 1913 observation of the Andromeda Galaxy and Hummason's iconic 1936 observations, but with color photography, in order to openly show the world these beautiful color spectra and to determine if the calcium and other recognizable absorption and emission lines are located in a different color of the spectrum? Beyond there being the problem that the 1936 calcium absorption lines do not appear shifted relative to the spectrum size, and the problem that Slipher and others did not appear to recognize that spectra position and size depends on light source distance, there is, in my mind, a problem with the speeds that these galaxies are thought to be approaching or receding away from us. How likely is it that a massive star or galaxy would be moving toward or away from us at speeds similar to the speed of a tiny light particle? That seems pretty nimble for an object far more massive than a light particle. And then to have the vast majority of galaxies moving away from us at those speeds. 20 years later, after World War II, in 1956, Hummason published at least 2 more sets of spectra of 5 increasingly distant galaxies. Still in black and white, these spectra showed a much clearer and larger change in position of what are claimed to be the calcium absorption lines. However, in one of the publications, the photos of the calcium absorption lines in the farthest 2 galaxies are not very clear, while they are very clear in the photo of the same galaxies in the other publication. It cannot be ruled out that there could be other explanations for these absorption lines. For one thing, not all galaxies show calcium absorption lines, and some must show pairs of absorption lines that are due to other elements. One major problem is that not everyone is familiar with galactic spectra. Most people do not have access to a 200-inch telescope, and only a few people on Earth routinely look at the actual color spectra of the many galaxies in the visible universe, in addition to looking at the spectra of many atoms and molecules. Given that there are so many galaxies and different kinds of elemental spectra, it seems possible that a person could pick and choose individual galaxy spectra that support a theory of shifted calcium absorption lines and reject any that do not. Beyond this 1936 and 1956 supposed spectral evidence for the theory that the universe is expanding, was the claim by Penzias and Wilson of Bell Telephone Laboratories in 1965, who won a Nobel Prize for their discovery of so-called background radiation, which is thought to be extremely Doppler-affected red-shifted light that originated from the very moment the universe was created. However, simple logic suggests to me, at least, that any light particles we detect with our tiny telescopes around planet Earth can only be from a comparatively nearby source. Beyond the source of those and all the other light particles we see, there must be billions and billions of galaxies of stars so far away, ladies and gentlemen, that we will never, ever see them. These galaxies are so far away that not one particle they emit can reach us because those light particles simply are not going in our direction, or they are absorbed by atoms in between us long before they reach our tiny, tiny region of the universe. Think of a simple campfire. The farther you walk away from the fire, the less you feel the heat. Johannes Kepler had found that the intensity of light from a light source to a viewer is lowered by the inverse distance squared in 1604, and so the amount of light we can detect from a light source drops off very quickly. If the visible universe we can see is only a tiny part of the universe, it seems logical that all the farthest galaxies we see would be similar, and in a similar setting as the closest galaxies we see are, and not speeding away at radically fast speeds. It is a little absurd to think that every time when astronomers build a bigger telescope that allows them to see more distant galaxies than they saw before, will they then proclaim that the universe just got bigger, and older too. A possible example of this is how the Webb telescope has recently identified some galaxies that are too large to be formed so soon after the theoretical beginning of the universe, according to the current theory. Many of you may not be aware that recently some scientists found another problem with the claim of an expanding universe, in that they found that distant galaxies are just as bright relative to their distance than closer galaxies are, which is not expected for a universe that is expanding. My doubt is personally increased when I see authoritative proclamations of absolute certainty for theories that are highly speculative.
According to Brian Cox, regardless of what you may have read or heard, the Big Bang is supported by a preponderance of evidence that has become the most successful theory ever put forth for the origin and evolution of the universe.
The tenets of the Big Bang, that the universe started out small, hot, dense, where matter and energy were a primordial soup, where the forces of nature had merged, all of that is thoroughly supported by observations of this universe.
I think a much healthier view was expressed by Carl Sagan around 1978.
There are few astronomers who doubt that the redshift of distant galaxies is due to the Doppler effect, who are skeptical about the expanding universe and the Big Bang. Perhaps our descendants will regard our present ignorance with as much sympathy as we feel to the ancients for not knowing whether the Earth went around the sun.
There was a time when people debated openly if space and time are infinite, like this insightful 1911 paper by Charles Ames, Are Space and Time Infinite? The affirmative answer. One last thought is that if these spectral lines are redshifted, that is, their frequency is lowered, it cannot be ruled out that this effect might be due to light being delayed by matter in between there and here. In 1923, Arthur Compton proved how reflected light can be lower in frequency than the source light is. This phenomenon is called Compton scattering. And in 1959, Pound and Rebka proved that the frequency of light can be redshifted just by the effect of gravity from another mass. But to me, the theory of an expanding universe, which was created from a single explosion that was close enough to us for us to still observe the light particles that were emitted from it, and that resulted in all the galaxies expanding away from it, seems doubtful. At the very least, these questions about the claim of an expanding universe and the perceived problems with this claim should inspire us to more closely examine the evidence, in addition to gather and make public more evidence in order to help flush out the actual truth.